Hello all, welcome to this course on time series modeling and forecasting using R. So now we're almost through with the entire course. We just have a couple of more sessions to go. And then the broad idea about this week was machine learning aspects in time series. So we started with a bit of an introduction in the first session. We sort of gave a flavor of different ML techniques which are used in practice and some applications and some integrations of each one of them with time series applications along with examples and so on and so forth. Then in the second session this week, we talked about particularly about three ML techniques, let's say regression, support vector machines, random forests, etc. And in the very last session, we talked about an idea called as k nearest neighbors, applications, limitations, advantages of KNN, right? And right towards the end, I gave you a very short flavor about a classification ML model called as naive Bayes. So now is the time to sort of discuss briefly and rather in detail about the idea called or rather the integration of neural networks and time series. Okay. So again, the heading has two important aspects inbuilt in that. So the first is neural networks, second is time series, and then how do you integrate the two? And what exactly are some of the models pertaining to or other having an integration of neural networks and time series, etc. Okay. So again, I've thought of putting some slides as an introductory slides to just to describe about generally about neural networks. So if you're not very confident about what do you mean by neural network, right? So these days you have very huge hype about all these terminologies, right? So deep learning, neural networks, AI, ML, etc. So we'll try to understand exactly what do you mean by a neural network outside of a time series context, and then of course we'll stitch the two things together. Okay. So as always, we'll start with a small introduction about the general idea about a neural network, right? So firstly, all the neural networks are artificial, right? So artificial neural networks are nothing but forecasting methods that are based on simple mathematical models of the brain. Okay? Secondly, they allow some complex nonlinear relationships between the response variable and its predictor. So again, when it comes to neural network, of course, it's capable of handling much more complex nonlinearity aspects or nonlinearity patterns as compared to some of the traditional ML methods. Okay? And hence, all these neural network ideas fall inside the umbrella of deep learning. So here in front of you, you can see a small image where let's say you're the nucleus. So this is an image of what goes inside a brain, a typical brain. So let's say, so in the center you have the nucleus, and then you have all these dendrites, and this is the axon, these are boutons, etc. But essentially the idea is that let's say how do you pass the information through all the neurons in the brain. So from the nucleus, let's say if you generate some information, and then how the information is getting passed through all the layers in the brain, which is called, and then through all the neurons in the brain. So if you try to mimic the exact same thing using some mathematical models, these are called as neural networks. Okay? So again, just to recap one more time, the neural networks are nothing but some forecasting methods which are based on simple mathematical models of a typical brain. And then secondly, they allow some complex nonlinear relationships between the response variable and its predictors. Okay? So sort of pick this image from this source, and if you want some more information, then one can actually visit the source here. All right. Okay. So secondly, we'll talk about what exactly goes inside the let's say neurons and how exactly is the information passed, and then how can we connect the two things together. So on one hand, you have the architecture of the brain. On the other hand, you have the actual mathematical model. So how do you stitch the two things together, and then how are kind of these two things sort of similar? So we'll discuss all these things now. Okay. So the second idea is what exactly is the architecture of the neural network. So a neural network can be thought of as a network of neurons. So let's say you have a strong network or a rather widespread network of neurons which are organized in multiple layers, right? So let's say you have all these multiple layers, and then the information has to be passed through all these layers, right? And then imagine again that you see inside somebody's brain, and then you're thinking that the information is getting passed through all the neurons originating from the, again if you go back a slide, originating from the nucleus. And let's say different sets of information are being passed through all these layers inside the brain until it reaches the output. Okay. So again, a neural network can be thought of as a network of neurons which are organized in different layers. The predictors or inputs form the bottom layer, and the forecasts or outputs form the top layer. Okay. So all these bottom layers, which are the layers below the very last one, so these are called as bottom layers. So all the bottom layers form the structure of the predictors or inputs, and the top layers. So top layers are nothing but the last layers, are nothing but the forecasts or outputs. Okay? There may also be some intermediate layers called as hidden neurons. So there may be some hidden layers like you've drawn here, and all these layers may be hidden. So you essentially don't know that how many layers are there, and then information is being passed through how many layers in between from the input layer and the output layer. Okay, so the very bottom layer is exactly where all the inputs are being passed, something like that, and this is the output layer. So the output is being pre-processed and then coming out of the output layer, and even in between the input layer and the output layer, there could be multiple hidden layers or hidden neurons. So essentially, this entire exercise and this entire idea loosely mimic the way our brains solve the problem. Let's say by taking in inputs, processing them, and generating an output. So the entire processing is done inside the hidden layers between the input and the output layer. Okay. So let's say imagine that the information is passing through the input layer, then the pre-processing or all the processing is been done, and the output is generated from the output layer. Okay. Like us, they learn to recognize patterns, but they do this by training on labeled datasets. So what exactly are the inputs here? Again, inputs are some labeled datasets. So they try to sort of mimic the labeled datasets, gain some information from the labeled dataset, pre-process or rather process the labeled dataset using the hidden neurons or the hidden architecture, and then provides an output. So hopefully, if somebody is not very confident about neural network, one should again read up, let's say, a small elementary book on that or see some videos on that. But broadly speaking, this is the idea that there goes some mathematical models inside the hidden layers that are capable of processing the inputs and throwing the outputs. Okay. Alright, so a very famous neural network is called as a perceptron. So we'll discuss briefly as to what you mean by perceptron. So the network of nodes sends signals in one direction, and hence it is called as a feed-forward network. So what do you mean by feed-forward? So the information only goes in one direction, from an input to all the hidden layers and then output. Something like this, then it's called as a feed-forward network. And the below figure depicts a neuron connected with n other neurons and thus receives n inputs. Let's say x1, x2, x3, x4 up to xn. Okay. So, and then this entire architecture is in fact called as a perceptron. So perceptron is a very elementary kind of a neural network which contains a feed-forward network where information is being passed in only one direction. And let's say you have all these sets of inputs, let's say n inputs, x1, x2, x3 up to xn. And then there has to be some sort of weight function. So again, don't worry. So we have all these ingredients one by one. So we'll talk about them one by one. So let's say inputs, then you have some weight functions given by w's. Then you take some sort of a sum. Then you have some activation function and eventually the output. Okay. So these all are the individual ingredients which sort of process the inputs and throws the output. So using the inputs, you bring in some weight functions. Then you take the sum or rather the weighted sum. Then you sort of involve some activation function of some sort, and once you sort of translate or transform using the activation function, then you're capable of throwing the output. Okay, but since this is a very classical sort of a neural network, it's called as a perceptron. So the entire architecture which is seen here is called as a perceptron. Okay? Now the second aspect, again, if you go back a slide, then after the input layer, you must implement some sort of weight functions to all the input layers. Okay, so second aspect of the second ingredient are the weights. So we start with an example. So let's say you bike to work. Okay, so you have to go to work using a bicycle, and you have two factors to make your decision to go to work. So should you go to work or not go to work is based on two factors. First factor is the weather. So weather must not be bad, of course. And second factor is it must be a weekday. So you won't go to work on a weekend. Okay, so you have to focus or rather control for these two factors. So weather factor and then weekday factor. So the inputs have to be binary. So let's propose the conditions as yes or no questions. And again, in this case, we can easily do that. So if weather is fine, then 1 for yes, 0 for no. And similarly, if it's a weekday, 1 for yes, 0 for no. So we're basically binary coding each and every factor here. So whether, if it's good weather, then 1. If it's bad weather, then 0. Similarly, if it's a weekday, it's 1. And if it's a weekend, it's 0. We cannot tell the neural network these conditions. It must learn them for itself. Okay. So what happens inside the neural network, we cannot tell specifically the neural network as to what condition it is. So based on some labeled inputs or labeled data set, the neural network has to understand by itself as to what weight functions one should choose. Okay. And essentially, the neural network does with something called as weights. Okay. So again, just to repeat, so in the context of this example, the neural network has to decide as to which factor. So whether the first factor, which is weather, or the second factor, which is weekday, should be given more weight. And again, it depends on which factor is important. Okay. So if the weather is important than weekday, then the weight function for weather should be higher, and vice versa. So if somebody thinks that being a weekday is more important than weather, then it should give more weight to weekday. Okay. So essentially, one has to balance the weights for each of the features or each of the inputs. Okay. So a higher weight means the neural network considers that input more important compared to the other inputs. And how it does this? So it will learn this by learning from the training data. So whatever labeled data sets or labeled features you're giving or throwing inside the input layer of the network, the neural network is capable of understanding the weight functions from the training data itself. Make sense so far? So second ingredient is weights. And then, so how do you train the perceptron? So training in the perceptron. So input vectors from a training set are presented to the perceptron one after the other, and weights are modified according to the following equation. So now we are slowly entering into small technicalities here. So again, we need not worry. So we'll not throw in lot of notations here, but just to understand the mathematical idea behind what goes inside training the perceptron, right? So for all inputs I, this is my Wi. So Wi depends on the current Wi plus A into G prime of sum of inputs. This is G prime of sum of inputs into T minus A into P of I. Now, what do you mean by each and every terminology here? So, firstly, G prime. So, G prime is nothing but the derivative of the activation function. Now, again, we'll soon see that what do you mean by activation function. This is one ingredient which is still remaining. A is called as the learning rate. W is the weight vector. We've seen in the previous slide what do you mean by W. So, W is a weight vector. P is the input vector. So, whatever features you're throwing inside the network. Capital T is the correct output that the perceptron should have known. And capital A is the output which is given by the perceptron. So imagine that you're training the perceptron by some features, by some inputs, and the perceptron is throwing some output, right? So capital T is the output that is expected. Capital A is the output which is given by the perceptron. So this sort of tells us the error, right? So how much is the difference between the expected output and the given output? So T minus A, and then P is nothing but the input vector. So you multiply by the input features, T minus A, and G prime is nothing but the derivative of the activation function, and then plus the weight function. Okay, so this is essentially the mathematical model which goes inside training the perceptron. So this is more like a training or other going back and forth sort of an exercise, right? So you keep on training the perceptron, trying to improve the accuracy, again go back, try to correct for the errors, again train the perceptron until the final output has a very high accuracy. Okay. So in general, the entire idea about any ML technique or deep learning technique, neural network technique, it considers lot of training which goes inside the particular model. So you have to correct the errors, you have to go back and forth, you try to correct the errors, again retrain, get the output, find the accuracy. If you still think that the accuracy is not good enough, then you again go back, again reweigh the options, try to correct for all the parameters there, again retrain, again get the output, and so on. So it's sort of an iterative procedure that goes inside any of the model there. Okay. So hopefully the idea about training the perceptron is clear, that what are the ingredients that go inside training any perceptron. Okay. Now the third ingredient and the most important one is the activation function. So what do you mean by activation function? So activation functions are nothing but mathematical equations or formulas that determine the output of a neural network layer given its inputs. Okay. So activation function is nothing but some functions which sort of transform the inputs or the mathematics behind the inputs and then give some desired output. So they introduce some non-linearity to the model, enabling it to learn complex patterns and relationships in the dataset. Okay. And again, don't worry, we'll discuss a couple of examples which are widely applicable activation functions. So first one is called a sigmoid activation function. And sigmoid activation function is useful for binary classification problems. And what exactly is the sigmoid function? So this is the sigmoid function. So 1 divided by 1 plus e to the power minus x. And then x stands for the input. So whatever input or feature you have, or the quantity of the input you have, you basically replace that value here. You find out the activation function, which is f of x, and then you approach towards the output. But why do you require the activation function? You require the activation function to translate all the inputs into desired outputs. Okay. Second most important or widely applicable activation function is tan H activation function. So hidden layer where the output needs to be zero centered, and then this is the activation function. So f of x is e to the x minus e to the minus x divided by e to the x plus e to the minus x. So these two are sort of similar if you find resemblance between a sigmoid function and a tan H function. So I'll say a tan H function is nothing but a slightly weird version of the sigmoid function. Okay. Now, what would happen if you don't have any hidden layers in the network? Then what? So if there are no hidden layers in the model reduces to what? So can you try to answer this question? So let's say if this is the architecture. So you have 4 inputs. So the input layer, and you don't have any hidden layers. You only have an output layer. So based on subsets of inputs, if you're throwing one single output, then the model reduces to, and the answer is regression. Okay. So if you don't have any hidden layers, the model reduces essentially to a regression sort of a idea. Okay, because again you can think that all these are individual predictors, so x1, x2, x3, x4, then you have some sort of a mathematical model that goes inside this, which sort of connects all the inputs together and tries to estimate the betas and throws one single output. Okay, so since you don't have any hidden layers in between, the problem reduces to sort of translating the inputs that you have, which are nothing but predictors, and then constructing that model and then throwing a single output. Okay, so the answer here is nothing but regression. So if you don't have any hidden layers, then a neural network reduces to a regression problem. And then a similar extension of that is what would happen if you bring in a hidden layer in between. So this is exactly how hidden layers are visualized. So you have this input layer here. Now again, assuming that you have 4 inputs, 1, 2, 3, 4, and then before you throw an output, you have this hidden layer in between. And remember one thing, that these are called as nodes, right? So each circle in any of the layers is called as nodes, by the way. So the hidden layer here contains 3 nodes, and if you see in this architecture, each node in the hidden layer receives inputs from all the 4 inputs. So can you see that? So you have arrows from all the 4 inputs pointing towards any of the node in the hidden layer. And this is a typical extension of what we saw earlier, a slide back, where you didn't have any hidden layers. So once we add a hidden layer or intermediate layer with hidden neurons, the neural network becomes non-linear, of course, right? And why is it called a hidden layer? Because you don't know what exactly is going inside this layer. You just assume that there is some hidden layer, you throw in the inputs, which is the input layer, there is some complex non-linear mathematical model which goes inside this hidden layer and is capable of throwing an output, basically. And such an extension or such an architecture is called as a multi-layer feed-forward network. So obviously why multi-layer? Because it contains more than one layer. So it contains several hidden layers as well. Now remember one thing, that there need not be a single set of hidden layer, there could be multiple also. So for example, there could be more hidden layers, for example here. Okay, so there could be hidden layer 1, hidden layer 2, hidden layer 3, etc. So more the number of hidden layers, the entire neural network becomes more complicated in a way. Okay? But the more important aspect here is that each layer of nodes receives inputs from the previous layers. And the outputs of the nodes in one layer are nothing but inputs to the next layer. So can you see that? So outputs coming from the input layer are nothing but input to the hidden layer. And again, the outputs from the hidden layer go to the output layer and throws a single output. Okay? So the inputs to each node are combined using a weighted linear combination. So there has to be some mathematical formula or mathematical technique to combine the information coming from, let's say, the input layer or the hidden layer, etc. Okay? So hopefully the general architecture should be clear as to what do you mean by layers, what do you mean by hidden layer, how the information passes through the layers, etc. Now we'll talk about one very famous model, and this is the place where we sort of integrate neural networks and autoregression or time series. Okay. So what would happen if you have a time series data? So with the time series data, lagged values of the time series can be used as inputs to your neural network, isn't it? So let's say if you want to predict yt, and then you have easy access to, let's say, its own lagged values. So yt minus 1, yt minus 2, yt minus 3, etc. So why not use all the lagged values as inputs to your neural network? Just as we use lagged values in a linear autoregression model. So when you create, let's say, an AR model, even there you have, let's say, all these along with the phi coefficients and a random error, right? If you remember the AR model structure. Similarly here, the idea is that we'll use all the lagged values as inputs to the in-between layers of a neural network. So hence we call this neural network autoregression or the NNAR model. So NNAR stands for neural network autoregression model. And here we're assuming a very simple case that we only consider feed forward networks. So what do you mean by that? So information passes in one direction only, and assuming it only has one hidden layer. So there's an input layer, one hidden layer and an output layer. And we use the notation NNAR P comma K to indicate that there are P lagged inputs. So P stands for you have P lagged inputs. So YT minus 1, YT minus 2 up to YT minus P, let's say in general, and K nodes in the hidden layer. So the second argument here stands for how many nodes are there in the hidden layer. So for example, so can you answer this? So what do you think this would stand for? So NNAR 9, 5. So in general, NNAR 9, 5 model is nothing but a neural network where the last 9 observations use as inputs for forecasting the output YT, having 5 neurons in the hidden layer. Okay. So let's say you have all these input layers, right? And the hidden layer only has 5 neurons. So 1, 2, 3, 4, 5, and then you have the output layer. So information is being passed from the input layer to all the, so this is the architecture that you have, and again from the hidden layer to the output layer, and it throws the output. So in the same spirit, can you try to answer this question now? So NNAR P, 0 model is equivalent to which model? So what do you think? So again, NNAR P, 0 means that you're using P lagged values as inputs, and you don't have any hidden layer here because the second argument is 0. So you have 0 nodes in the hidden layer. So essentially this model is nothing but ARMA P, 0. So essentially this model is nothing but ARMA P, 0, or rather ARIMA P, 0, 0. Okay. So an NNAR P, 0 model reduces to nothing but ARMA P, 0 model. So hopefully I've tried to explain a very elementary sort of a connection between neural network and time series by bringing the idea of a NNAR P, K model. Now there's one more ingredient, or rather one important aspect which has to be controlled when it comes to neural networks, which is called as batch, iterations and epoch. So what do you mean by that? So what do you mean by batch? What are iterations? What do you mean by epoch? So we'll try to understand this one by one. So what happens is, let's say if you have a very big data set, one cannot pass the entire data set in a neural network at once. Okay. So what can we do? So we have to divide the entire data set into small parts, which are called as batches. Okay. So we cannot pass the entire data set into a neural network at once. So we have to divide the data set into number of batches or smaller sets or parts. Hence, the batch size is a hyperparameter that defines the number of samples to work through before updating the internal model parameters. So batch size, so how many observations in one batch, how many batches should there be? So all these are hyperparameters that have to be controlled before updating the internal model parameters. And then what do you mean by iterations? So iterations is nothing but the number of batches needed to complete one full cycle, and then one full cycle is called as one epoch. So essentially one epoch is when an entire data set is passed forward and backward through the neural network only once. So once you exhaust all the observations that are there in the entire data set, then that is called as a one epoch. And usually what people do is they sort of pass the entire data set number of times. So they have number of different epochs, or let's say 100 epochs or 500 epochs. And why exactly? So let's say you run the entire data set, of course, by dividing them into batches and form all the epochs. And you run the entire neural network exercise 100 times or 500 times or 1000 times. And then you take the average. Okay. And why exactly? Because doing the entire exercise just once sort of cannot give a very clear picture, right? I mean, since you don't know what's going inside the neural network, it's completely black box. So it's obviously a very good idea to sort of repeat the entire exercise number of times and take the average. Okay. So let's say if you repeat the entire exercise 100 times, then you have 100 epochs. Or if you repeat the entire exercise, let's say 500 times, it's called as 500 epochs, and so on. Okay. So again, this is a very important idea when it comes to neural network, that once you divide the data into number of smaller parts called as batches, and you run the batches, and once you exhaust all the batches or the entire data set, it's called as one epoch. Okay. Now, of course, use of more than one epoch, why exactly? So since we're using a limited data set and to optimize the learning, we're using a gradient descent, which is an iterative process. So updating the weights with single pass or one epoch is not enough. And then obviously one epoch leads to underfitting. So if you only use one epoch or pass the entire set of observations only once, then it's a rather underfitting. As the number of epochs increases, a greater number of times the weight are changed in the neural network, and the curve goes from underfitting to optimal to overfitting. So again, the number of epochs that one should run the entire network for is again a hyperparameter which has to be balanced somewhere. So one should not again go too overboard. So one should balance or strike a balance between underfitting and overfitting. Okay. Now towards the end of this session, we'll see a very briefly a practical application in R, and of course the next session is entirely practical. But so we have in front of you, we have an USD INR exchange rate from let's say 3rd April 23 to 29th March of 24, and this is exactly how the exchange rate behaves. So on April, or rather 3rd April of 2023, the exchange rate was close to 83.5, and then it sort of dropped down to 82 and so on and so forth. So USD INR exchange rate over this timeline. Okay, and now we'll see that can we fit some sort of an NNAR model on that. Okay, so first the ACF plot. So ACF plot is rather non-stationary. So what should be done? So one should either transform, take the difference, and so on. Right. So since all the spikes are significant and away from the bounds, then we can safely conclude that the series is highly non-stationary. And of course, one can use the augmented Dickey-Fuller test to test that. So again, all these have been covered well back in the course. Okay, so again, if you're not very confident, then you should go back and then try to revise. Okay, so here if you see the p-value is more than 0.05, hence we cannot reject the null. And null hypothesis is the series is not stationary. Okay, so what do? I can difference the plot once. So time series plot of the exchange rate differenced once. And now essentially one can see that the stationarity has improved from the earlier plot. Okay, so again if you run the ADF test on the difference plot, now the p-value is within the range. So 0.01 is less than 0.05, let's say. So one can actually reject the null and conclude that the series is stationary. So now then what? So then we can implement, or rather put forward an NNAR model with one hidden layer. Okay, so let's say you have one hidden layer in between. And which model are we training the data set on? So we'll train the data set on NNAR11 model. So again, what do you mean by 1-1 model? We'll use only one past value as input, so YT minus 1 only. And in the hidden layer, there'll only be one node. Okay, so let's say if you have the input layer, then you have the hidden layer having one node, and then the output layer, something like that. And then you take the average of 20 such networks. So we're taking 20 epochs here. Okay, so this number means 20 epochs. So you run the entire exercise 20 times, you take the average of that, each of which is a 1-1-1 network as specified here with 4 weight options. So one can choose the weight options, and this entire exercise has been done in R, by the way. And here you can see that it throws you some estimates. So sigma square is estimated as 0.01438, etc. And these are the forecasts along with the accuracy measures. So here you can see that the forecasts are not very good, right? So by the way, the forecasts are given by this horizontal blue line, which is obviously not matching the pattern of the exchange rate. So we can improve, but I've only included this exercise just to make you all understand as to how do you implement the NNAR in R exactly on a practical data set. And along with here, we can see that, let's say how much is the root mean square error, or how much is the mean square error, MAE, all those values. Okay, so hopefully the idea of neural networks is clear, and then the integration of neural networks to time series is clear, and then we discussed one very important model called as NNAR, and then the idea about, let's say, how do you implement on a practical application in R is clear. Okay, thank you.